Welcome back to DeepVisus, where vision meets depth. I'm your host, and in today's episode, we're building on our previous discussion to explore how we can actually create intelligent systems. Our source for this deep dive is part 2 of Understanding Intelligence by Rolf Pfeifer and Scheier, titled A Framework for Embodied Cognitive Science. Last time, we uncovered the fundamental problems that plagued classical artificial intelligence, or AI, particularly its struggle with real-world interaction. This leads us to our central question for today. How can we design and build truly intelligent systems that interact meaningfully with the complex, unpredictable real world, moving beyond the limitations of abstract, symbolic approaches? Pfeifer and Scheier propose a new framework centered on what they call complete agents. Think of these as systems, whether biological or artificial, that are capable of surviving and behaving autonomously in the real world without constant human intervention. They are complete because they integrate all the necessary capabilities to do so. The authors introduce the evocative metaphor of fungus eaters, simple creatures that must forage for energy and navigate their environment independently. This scenario highlights several crucial properties of complete agents. First, autonomy. This refers to an agent's independence from external control. It's not an all-or-nothing concept, rather, it's a matter of degree. An agent with more autonomy can make more decisions on its own. Second, self-sufficiency. This means an agent can sustain itself over extended periods. It must manage its own resources, like energy, and avoid irrecoverable deficits, situations where it can no longer maintain its basic functions. This often involves making trade-offs between different behaviors, such as foraging for food versus avoiding predators. Third, situatedness. A situated agent acquires all its information about the environment directly through its own sensors from its own unique perspective. It doesn't rely on predefined, human-interpreted symbolic representations. Instead, it directly interacts with the world. Fourth, and perhaps most foundational, is embodiment. This means the agent exists as a physical entity with a body, sensors, and motor systems. Intelligence, in this view, doesn't just reside in a brain or a central processing unit. It emerges from the dynamic interaction of the entire organism with its physical environment. This allows the agent to exploit the inherent physics of the world, often simplifying complex problems. Fifth, adaptivity. This is the ability to maintain structure and function in continuously changing and unpredictable environments. It's a direct consequence of self-sufficiency. The book discusses various kinds of adaptation, from long-term evolutionary changes to rapid sensory adjustments and, most importantly for our discussion, adaptation through learning. Finally, agents are always designed for a specific ecological niche, the range of environmental conditions they can exist and operate within. Just as there's no universal animal in nature, there's no universal robot. Exploiting the specific constraints of a niche can greatly simplify design. To study these complete agents, the authors advocate for a synthetic methodology, which means understanding by building. This involves creating artificial agents, either robotic agents, physical robots like the Mars Sojourner, or models of insect behavior, or simulated agents that exist in virtual environments. Both have their uses, but the emphasis is on physically realistic interaction. A key challenge in this design process is the frame of reference problem. This highlights the critical distinction between an observer's description of an agent's behavior and the agent's internal mechanisms. Often, what looks like complex behavior to an outside observer might arise from surprisingly simple internal rules interacting with a complex environment, as illustrated by the famous example of Simon's ant walking on a beach. This means we must design for emergence, where behaviors are not explicitly pre-programmed but arise spontaneously from the agent's interaction with its environment. This involves focusing on low-level specifications of the agent's physical setup rather than high-level, human-defined ontologies. So, how do we build these agents? Chapter 5 introduces neural networks as a powerful tool. Inspired by biological brains, neural networks are robust, intrinsically learning systems that can generalize. They are massively parallel, meaning many processes can happen simultaneously, which contributes to their fault and noise tolerance. The authors break down neural networks into their basic components: nodes, connectivity, propagation rules, and learning rules. Crucially, for embodied agents, we must also consider how the network is embedded within the physical robot, connecting to its sensors and motors. A prime example is the distributed adaptive control architecture. Here, a robot learns to avoid obstacles and seek light sources. It uses a type of learning called Hebbian learning, often summarized as neurons that fire together, wire together. When the robot's collision sensors activate simultaneously with its proximity sensors, the connections between the corresponding neural network nodes are strengthened. Over time, the robot learns to anticipate obstacles, turning away before it actually collides. This anticipation isn't a complex internal plan, but an emergent property of simple associative learning, exploiting the redundancy principle. The correlation between different sensory inputs from its physical interaction with the environment. This system learns continuously without a separate training phase and even incorporates active forgetting to prevent weights from becoming too large. The chapter also distinguishes between different types of neural networks. Non-supervised networks, like the distributed adaptive control, learn without a teacher providing correct answers. Supervised networks, like NET-Talk, which learns to pronounce English text, require explicit correct output for training, and reinforcement learning, where the system receives feedback, rewards, or punishments, but must figure out the correct actions itself. A critical polemic in the book argues that even powerful supervised neural networks, like NET-Talk, do not solve the symbol grounding problem. Their inputs and outputs are still based on human-defined, high-level ontologies. True intelligence and the grounding of meaning only occurs when the neural network is embedded in a physical robot that directly interacts with the real world. In this setup, the robot's movements have direct meaning to the robot itself because they affect its sensory input and subsequent behavior. This is the shift from pure information processing to a truly embodied approach. So, to answer our question, building truly intelligent systems that interact meaningfully with the real world requires a radical departure from classical AI. It demands designing complete, autonomous, self-sufficient, situated, and embodied agents that operate within specific ecological niches. Neural networks are a powerful tool for this, but their intelligence emerges not from abstract computation alone, but from their direct, physical interaction with the environment, allowing for continuous learning and the grounding of meaning in experience. That brings us to the end of our deep dive into part 2 of Understanding Intelligence. Next time on DeepVisus, we'll continue to explore the fascinating world of brain, mind, and intelligence. So, stay tuned.